Okay, let's do a quick Newton's Law problem. Let's say that you're standing on a scale on an elevator. It's a bathroom scale, it's a spring scale. And let's just say we know that your weight is 550 newtons and the scale is accurate. And the elevator is able to move up and down. And let's just say that you're going up from the ground floor to a higher floor. And you should probably understand that elevators accelerate from rest, like if they're starting from a floor for a very short amount of time, then they typically travel at constant speed. And then they accelerate again to come to a stop, right? Acceleration means speeding up or slowing down. So they're going to speed up, travel at constant speed, slow down, come to a stop. Okay, so let's just say that the elevator is accelerating upwards at 2 meters per second squared. Let's ask, what does the scale read? So how are we going to address this problem? You should probably stop, think about it, try to set it up for yourself, but I will go on. What we want to do is we want to draw, in order to make sure, you might know the answer to this, you might think you know the answer to this, but in order to be careful, I'm going to draw a free body diagram. So this is U on an elevator, okay? So this is U. I'm going to just, again, approximate U as a little box and draw a free body diagram. What are the forces on U? Go through our list of forces, FG, Fn, Ft, Ff, F push, F spring, and of all of those, we'll go through the list. You say, okay, there's gravitational force in what direction? It's in the downward direction. That's your weight. What else? Basically, there is nothing else touching you except for the scale. So, and that is a normal force, and it's in the upward direction. So you can call it F scale or F normal. Okay, F normal. And that is a correct free body diagram. It's always the things that are touching you plus gravity. Okay, so those are the forces. Now, in order to solve this as a Newton's second law problem, we know that we got to choose our positive direction. So which direction do we want to choose as positive? Since the it's always a good idea to choose your positive direction as the direction of acceleration. Sometimes, you don't have to do that, but it's a good rule of thumb. So I'm going to choose that as my plus x direction. I'm going to write down F net equals ma. I'm going to say, it's just a one-dimensional problem, so all I have to do is the net force in the x direction equals m times a in the x direction. If there was a y force, we would also have to do the y direction. And we can say that we evaluate the net force in the x direction from the free body diagram. So that's plus Fn minus Fg equals, so that's the left-hand side. The right-hand side, your mass times your acceleration. In this case, the acceleration is given as 2 meters per second squared. I'm writing this all as letters first, where we know Fg is equal to 550 newtons. We know A is equal to plus, because it's in the positive direction, 2 meters per second squared. And we know M, right? What's M? I didn't leave myself space. I'm just going to write it in a corner. Sorry. We can write it underneath here. Therefore, mg equals 550 newtons. So m equals 550 newtons over 9.8 meters per second squared. And then we can plug everything in. We know everything in this equation, Fg, m, a, and we don't know Fn. So we can solve for Fn. But how does that help? How does that help? Well, we're solving for the normal force, which is what? The normal force is the force that the scale exerts on me. But what does that have to do with what the scale reads? Because that's not a force on the scale. That's a force on me. Again, I'd like to give you time to think about that, but I'll give you the answer. The answer is by Newton's third law. If Fn is the force that the scale exerts on me, then I must exert that same force on the scale. So the scale actually reads Fn. Now that's Fn in the downward direction. The force on the scale is Fn in the downward direction by Newton's third law, but that's what the scale reads. So the scale actually reads Fn. That's the value the scale reads. The normal force that the scale exerts on me is equal to the normal force I exert on the scale. So we can go ahead and solve for Fn and say, okay, therefore Fn is equal to, I got to look back, ma plus Fg, or I'm going to write it this way, Fg plus ma, which is 550 newtons plus 550 newtons divided by 9.8 meters per second squared. That's my mass. I just never did the number out. Times the acceleration, which is plus 2 meters per second squared. So you plug in those numbers, and I only kept 3 significant digits. If you keep more, that's okay, just don't keep a lot more. And we get 662 newtons. So the scale reads something heavier than my weight. That's important to understand why. The scale reads something heavier than my weight. So you might realize if the elevator was sitting still, what would the scale read? Let's say part B. If the elevator is moving at, if the elevator was sitting still, what does the scale read? The scale will read 550 newtons. Acceleration is 0, Fn equals Fg, or you just say, oh, well, if I'm sitting still, scales read the right thing. 550 newtons. But if I'm accelerating upwards, if the elevator is accelerating upwards, basically I am being pushed into the scale. Nope, that's wrong. That's wrong. The scale is being pushed into me because the elevator is being forced upwards. The scale is being pushed into me, so the scale is going to read something bigger. But what's the result? The result is that the scale reads 662 newtons, and that means that I feel heavier. It means that I feel heavier, right? When you accelerate upwards, you feel heavy. All right, so how does the scale read when the elevator is traveling at constant speed? Well, this is where you need to realize that we can go ahead and do the same analysis here, but A is equal to 0. If it's traveling at constant speed, then A is equal to 0. Therefore, Fn minus Fg equals m times 0. Going through the whole same analysis, but I'm just skipping the steps up until that equation. And so therefore, Fn equals Fg. Therefore, the normal force on me, which is the force the scale exerts on me, which is the force that I exert on the scale, which is what the scale reads, is equal to my weight. Or your weight. Sorry, this is you. Your weight. And that might have been obvious. But why I wanted to ask this question is because whether you're traveling at constant speed or whether you're sitting still at no speed, the scale reads the same thing, right? It reads 550 newtons. Whether the elevator is sitting still or whether it's moving at constant speed, it reads 550 newtons. This is an example of the inertial reference frame, right? You're in an inertial reference frame. In an inertial reference frame, the physics should not change. In other words, if my weight is 550 newtons in one inertial reference frame, it better be 550 newtons in all inertial reference frames. Physics doesn't change in inertial reference frames. This was a non-inertial reference frame where, and you didn't need to recognize it, but I'm just going back to that concept, where the force, where my weight changes. Strange, isn't that strange? My weight changes. Well, if you look at it from an inertial reference frame, you know your weight doesn't change. The scale is being squished up into you. Okay, anyway, you don't need to recognize that here, but it's good to remember that inertial versus non-inertial. Let's ask what the scale reads if the elevator is accelerating downwards. I do want you to just get the concept here. If the elevator is accelerating downwards, it doesn't mean it's moving downwards, right? The elevator could still be moving up, it's just slowing down in the upward direction. So we said the elevator is going from a lower floor to a higher floor, but it's got to slow down when it gets to the floor that it's going to stop on. So at that point, the acceleration is downwards, right? That's, when it's slowing down. Okay, or it could have turned around and started moving downwards and speeding up in the downward direction. Either way, it's accelerating downwards at A equals 2 meters per second squared. So now you say, so now it's accelerating downwards instead of upwards. Do I have to change the direction of plus x? You could, nothing wrong with that. Or you could just put in A equals minus 2 meters per second squared. So we could actually just say plus x is in the upward direction. This is a time when we're saying, we're gonna flout the restriction, or not the restriction, the advice that you say plus x is the direction of the acceleration, and say we're just going to leave it because we already defined plus x is up, and it's illustrative in this case to say, well, therefore, if plus x is still up, then I'm going to say A is minus 2 meters per second squared because it is down. Whoops, careful. It's 2 meters per second squared down. Oh, let me rewrite that and be careful. 2 meters per second squared down, therefore, we can say A is minus 2 meters per second squared. Okay, it's not minus that 2 meters per second squared down because then it would be up. Okay, so if we do that, then we've still got the same equation where A is, instead of being 0 or 2, the same equation, A is now negative 2. Do it any way you please. You can change the positive direction and reanalyze it, but you're going to get the same thing. Fn minus mg equals ma, where a is minus 2 meters per second squared, and everything else is the same. So therefore, we're going to get this. And again, I just haven't bothered plugging in for mass. I just keep leaving mass as 550 newtons over 9.8 meters per second squared because that is your mass. And so we're going to get 550 newtons minus the 112, which gives me 438 newtons. Did I do that right? 138 newtons. So what happens when the elevator is accelerating downwards? When the elevator is accelerating downwards and I'm in that accelerated reference frame, I feel lighter. Am I lighter? Do I weigh any less? The scale reads 438 newtons. Does that mean I weigh less? It depends what you define by what does it mean to weigh something. I still have the same mass. I still would have the same weight. If we define weight as what you get in a scale that's on a fixed earth that's not accelerating, then indeed my weight is still 550 newtons. This is really what's called effective weight. So again, this is the normal force, which is the force that I exert on the scale, which is what the scale reads. What the scale reads is effective weight, where my weight is still 550 newtons, defined by mg. My effective weight is how heavy I feel. Because I'm accelerating downwards, I feel lighter. Because I'm accelerating upwards, I feel heavier. I feel effective weight. So, what if I accelerate at 9.8 meters per second squared down? What do I get? What is that? If the elevator is accelerating downwards at 9.8 meters per second squared, what do I get? I get that the normal force on me is 0. What that means is I'm no longer in contact with the scale. If the normal force is 0, that means you're not touching it. That's what 0 means for a normal force. A normal force is contact between two things. So there's an important concept by itself. That's what a normal force of 0 means. If you're not in contact with something, that's your normal force. But what it also means is that the scale reads nothing. So how heavy do I feel? I feel weightless. I feel like I have no weight. That is the definition of weightless. Right? Weightless simply means that you are accelerating downwards at 9.8 meters per second squared. On the surface of the Earth. I guess if we were on the moon, we'd be accelerating downwards at whatever the acceleration due to gravity on the moon is. But anyway, that's what weightless means. And we've discussed this before in this class, that weightless for an astronaut doesn't mean there is actually no weight. It means that they are falling at the acceleration due to gravity. Okay, bye-bye.